All right, we've now gone through all of the trig identities. We're done with chapter 5. And so here's the typical trig identities sheet. We've covered the derivation of all of the identities shown here, except for, on some trig identities sheets, they might include additional things like here's the conversion formula going from degrees to radians, and here's just a statement of the periodicity of the trig function. So if you take any of the trig functions and shift it by, any integer multiple of 2 pi, or for tangent and cotangent just pi, you get the trig function back. So we didn't explicitly talk about this as far as like a derivation, but these are obvious. But outside of these periodic formulas and just like the conversion factor from degrees to radians, we talked about all of these identities. Okay. Now in the process, there were questions that came up regarding, so for example, here's the sum and difference formulas for sine, cosine, and tangent. Well, okay, what about the sum and difference formulas for secant, cosecant, and cotangent? And the majority of the time when those questions came up, the answer was that you just had to think about the reciprocal. So if you took the reciprocal of sine of alpha plus or minus beta, you get the sum and difference formulas for cosecant. Same with cosine for secant, same with tangent for cotangent. Just flip this, right? And then even like for these product to sum formulas, which were a little more complex, you could still think about dividing by, take sine alpha times sine beta, divide that by cosine alpha times cosine beta, which is this, and you're left with tangent of alpha times tangent beta. So you just divide this by this. Okay? With these half angle formulas, you could take the reciprocals and get, for sine squared theta, you could take the reciprocal and get cosecant squared theta. And, even with these, the double angle identities, you could, take the reciprocal of this and you're left with cotangent 2 theta, right? Now, there was a question that came up when it came to the sum to product formulas, because all of a sudden it wasn't quite so simple to just say, well, if you wanted sine, so we have sine alpha plus sine beta. If you want tangent alpha plus tangent beta, then just divide sine alpha sine beta by cosine alpha plus cosine beta, and you get tangent alpha plus tangent beta. Well, no, you can't do that, right? Sine alpha plus sine beta over cosine alpha plus cosine beta is most certainly not equal to tangent alpha plus tangent beta. So you can't really do that here. And I mentioned I was going to look into what's the idea for if you wanted like tangent alpha plus tangent beta, etc. What are those identities? And so really what's going on is that there are more trig identities than what you'll see on a typical trig identities sheet. If you Google it, or that, the typical trig identity sheet that is going to contain these trig identities, and which is all the ones we derived in the general trigonometry textbook, right? These are all the ones you derive in a typical trigonometry course. However, if you're a major in mathematics, there's more trig identities. So there's also the triple angle formulas. So sine of 3 theta, cosine of 3 theta, tangent of 3 theta. Okay? And so the answer to the question of, well, what is tangent alpha plus tangent beta? That's just another trig identity. You have to derive that. It's not some simple just take a reciprocal. Okay, so just so we can take a look at it, let's derive tangent alpha plus tangent beta, or a trig identity for tangent alpha plus tangent beta. So, all right, tangent alpha plus tangent beta. We're wanting to get a sum to product formula for this. So we want to make this equal to something that contains no sum or difference of trig functions, but strictly just only products or division. That's that. We want to create a sum to product formula for tangent alpha plus tangent beta. All right, so we can start by writing this as sine of alpha over sine of beta plus, or no, sine of alpha over cosine of alpha plus sine of beta over cosine of beta. All right. Now let's create a common denominator, multiply this by cosine of beta over cosine of beta, and this by cosine of alpha over cosine of alpha. So we haven't changed anything, right? And we get, so let's see, that's going to be sine of alpha cosine of beta over cosine alpha cosine beta plus, okay, then cosine alpha cosine beta cosine alpha sine beta. So there's a common denominator. So we've got sine of alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta. Okay. Now this sine alpha cosine beta plus cosine alpha sine beta, that should look familiar. If we look here, that's sine of alpha. That would be, it was plus, was it? Plus, so that's sine of alpha plus beta. Sine of alpha plus beta is sine of alpha cosine beta plus cosine alpha sine beta. So we've got sine of alpha plus beta and there you go. That's it. That's what you'll typically see for the product to, or to the sum to product formula for tangent, right? We've got, this is sine of alpha plus beta. It's a trig function divided by the product of two trig functions. There's no summing of trig functions or subtracting. Now we could also, if we derive for the minus, we would get this. So tangent alpha minus tangent beta is sine of alpha minus beta over cosine alpha cosine beta. Okay, and so that's just an example. If you wanted to get us a sum to product formula for secant, cosecant, cotangent, you have to kind of go derive it on your own. You can't just, in this case, there's no just doing a reciprocal. That's not going to work. Now, again, it does work out to where you can just, we talked about this, you can just do reciprocals in this case. The reciprocal of cosine alpha times cosine beta is going to be secant alpha times secant beta because, right, 1 over cosine alpha times cosine beta, that's, you can write that as 1 over cosine alpha times 1 over cosine beta, which is secant alpha times secant beta. So you can just take the reciprocals in that case. And in most cases, that's how it worked out. But it's not always necessarily like that. Or maybe there's a product to some formula that you can't get by either taking this reciprocal or just dividing by, it looks like you could get anything you want. Like you could divide this, you could take sine alpha times sine beta and divide that by cosine alpha times cosine beta, which you have here, and you get tangent alpha times tangent beta. Or you could, and take the reciprocal of that, you get cotangent. So, but maybe if you wanted like secant alpha times, or okay, maybe sine alpha times tangent beta. Yeah, there you go. That's a good example. Sine alpha times tangent beta. You'd have to go to derive that. You'd have to go to the derivation of go to the video on how these were derived and use just like maybe like a parallel method, or maybe you can't derive it. I don't know. But if you want to see if you could derive something, you'd have to just play with it. Use all the trig identities that you already know in algebra to just play with it, kind of like we just did with tangent alpha plus tangent beta. Okay, now the triple angle identities, that's additional identities. Let's take a look at what's the triple angle identity for sine. So sine of 3 theta is minus 4 sine cubed theta plus 3 sine theta. There's the triple angle identity for sine. Now again, you could take the reciprocal of this and get the triple angle identity for cosecant. So the reciprocals work out nicely here. But, you know, how would you think we would derive this? Well, okay, we could start with sine of 2 theta plus theta. Okay, the sum formula for sine is what? Sine alpha plus beta, sine alpha cosine beta plus cosine alpha sine beta. So sine 2 theta cosine theta plus cosine 2 theta sine theta. Okay, now we can use the double angle formula for sine and cosine. So let's see. So sine of 2 theta is going to be 2 sine theta cosine theta. That's the double angle formula for sine. And then cosine, we've got 3 options to choose from. Let's do the one that involves sine, since it looks like we're trying to convert this to pure sine. So 1 minus 2 sine squared theta. So 1 minus 2 sine squared theta sine theta, since it looks like we're trying to get all sines here. So, okay, 2 sine theta cosine squared theta, and then plus sine theta minus 2 sine cubed theta. Okay, let's now convert that cosine squared to 1 minus sine squared. Okay, so 2 sine theta minus 2 sine cubed theta plus sine theta minus 2 sine cubed theta. Okay, so we get minus 4 sine cubed theta. You have minus 2 times minus 2, and then 2 plus 1 plus 3 sine theta. There you go. And there's more trig identities than just the triple angle identities. You have to go look into, you know, the more advanced math and see all the different trig identities that exist. But I just wanted to note that there are more trig identities than what you'll see on a typical trig identities sheet.